Okay, welcome to part 5 of our discussion of the atmosphere and storms. Now let's take a closer look at the different types of storms, how they form, as well as the damage they can cause. Now write in your notes that storms happen because of the meeting of a warm and a cold front, and that they need a constant source of energy, which is normally heat, in order to form. So when we're discussing storms, in the back of your mind, be thinking to yourself, what is the source of the heat or energy in this type of storm? And not only that, what is it that causes the storm to stop? So in your mind, you got to be thinking storms stop because somehow the energy gets drained out of the storm, and you'd be correct. So let's see how these storm mechanisms work. First, write in your notes that a storm is a violent disturbance in the atmosphere, and that there are 4 major types of storms that we're going to talk about. Let's get them in your notes. Thunderstorms, tornadoes, hurricanes, and our favorite, the winter storm. Also write that the scientists who study weather and try to predict it are called meteorologists. And they have one of the best jobs in the world because they can be wrong most of the time and still collect a paycheck. Let's start with thunderstorms. Write in your notes that a thunderstorm is a small storm, relatively speaking, often accompanied by heavy precipitation and frequent thunder and lightning, and that they form in large cumulonimbus clouds, and here you see a big one right here, and here you see one right here, just the one over here on the side, but here's a great picture of a cumulonimbus cloud. These are also called thunderheads, so get that in your notes. They're called thunderheads. Now they don't always produce thunder. You'll see cumulonimbus clouds that don't produce thunder, but most of the time, if you see them, there's a thunderstorm forming somewhere. Now, normally these form on hot, there's the heat, humid, there's the water, afternoons. So typically, you probably knew this, they don't form in the winter. See what I did there? Okay. So, now you got to be thinking to yourself, okay, thunderstorms, we don't have that many of them here. Why? Well, just think to yourself what our climate's like, and you'll get an idea of why we don't get thunderstorms. And we'll talk about those here in a second. Okay, now let's look at how thunderstorms actually form. Write in your notes that warm, humid air rises rapidly and the air cools, forming dense thunderhead clouds called cumulonimbus, and that heavy rain falls, sometimes along with hail. And you see a pretty doggone big hail size, or big size hailstone right here. Also write that within the thunderhead cloud, there are strong updrafts. Now here you see the updraft right here. There are strong updrafts and downdrafts. Again, you see the downdrafts now here and here. So when you have an updraft and a downdraft, what does that look like? That looks like convection to me. So you get literally convection currents flowing inside this thunderhead or cumulonimbus cloud. So write that in your notes. So this is really very similar to convective motion like in the rock cycle and the other examples we've talked about. Now, as you can see, this diagram also explains how hail forms. Write in your notes that hail is raindrops that are constantly being frozen and refrozen in a cloud due to a strong updraft. So you see here now these little balls now of essentially what started out to be rain. See the raindrops? And now they're stuck in this little convection current. And each time now they are pushed up into the cloud, they refreeze. So as they refreeze, they get bigger. So that's why when you cut open a hailstone, like you see here in this picture, you can see layers. You can actually count the number of times this hailstone was pushed back up and down and refrozen into a larger object by examining the rings, just like you do on a tree. So these rings now give a great idea of how many times that raindrop was refrozen into a hailstone. So the size of the hailstone gives an idea of how many times that has happened. Now, as you know, thunderstorms frequently produce lightning. Otherwise, they wouldn't be called thunderstorms because thunder is a result of lightning. So you sometimes you hear them called lightning storms, but typically they're called thunderstorms. Now let's take a look how lightning forms and just some different forms of lightning. Now let's write this formation in steps to make it easy for you to study. Okay, so in step 1, electrical charges build up in clouds because wind causes electrons to rub together. So you see that here in this picture. You see now the negative charges in the clouds and the positive charges in the ground. That's caused by the wind separating them in the clouds. Now, as they rub together, these electrons are rubbed off, all right, in the cloud, and these positive charges accumulate on the ground. Now, sometimes they can actually accumulate in the cloud. You see that here. Here's our positive charge, and here's our negative charge. Now, so we're going to talk about ground to cloud lightning, and we're going to talk about cloud to cloud lightning. So you can see why that lightning has the potential to form. So in step 2, the negative charges in the clouds push the negative charges on the ground away. They repel each other, leaving only the positive charges on the surface. That's what you see here. So these negative charges repel each other, and boom, they all accumulate here, and now the positives all accumulate down here. Then in step 3, once enough negative charges have built up in a cloud, it repels so strongly, repels meaning in this direction, it repels so strongly that these charges jump through the air and strike the positive charge ground of the nearest objects. So you see that happening right here. So what happens now is lightning is a dense stream of electrons. Write that in your notes. A dense stream of electrons, and that's what you see here. And boom, once there's enough of these charges that built up, they jump now to the ground. Why? Well, they jump to the ground because opposite charges attract, correct? So what you're seeing now is this giant mass of electrons now, boom, jumping down to the ground. You see that here. And literally, this is a dense stream of electrons that are now being discharged into the ground. And actually, this is a pretty cool picture of double lightning. So the same thing can happen inside a cloud like you see here. So in your notes, write that there are 2 basic types of lightning. There is cloud to ground lightning, and then inside the clouds, there's cloud to cloud lightning. So lots of times you can look up during a thunderstorm and you can see lightning happening inside a cloud because the cloud kind of lights up. But you don't see any like big streaks happening out of it. Typically, the ooh and ah lightning now is the cloud to ground lightning, and that's the really damaging one because if you happen to be on the ground, you can be the positive charge that attracts the lightning, and that people get hit by lightning all the time. So buildup of charges, negative, positive, then a jump of electrons. This negative charged electrons from cloud to ground, but it can also happen from cloud to cloud. As you might expect, there's lots of different kinds of lightning, and here's a list of them. I mean, there is no reason for us to memorize the many different kinds of lightning, but there's lots of them. And many of you ask about heat lightning because we hear about it all the time. That almost never happens here. Why? Because it's really never that hot. If we happen to get a hot summer, Boy, that's a distant memory. Then it's possible, but typically we get sheet lightning and spider lightning. So those are the typical kinds of, we don't get a lot of lightning here because we're in a cool area. But here are the different kinds of lightning. There's lots of them. Okay, so that's lightning. Now what about thunder? First, write in your notes that it's lightning that causes thunder. So when someone's, talking about thunder and lightning, you got to straighten them out and say, listen, the thunder is a result of the lightning, for example, that you see here. It's a pretty cool shot of a bolt of lightning hitting a building. I guess it wouldn't be cool if you were in the building, but so you simply can't have thunder without lightning. So first, let's explore why. Write in your notes that lightning heats the air around it to about 30,000 degrees, like it says right here. So when you see a bolt of lightning, all right, that air right just adjacent to that lightning instantly gets superheated to 30,000 degrees Celsius. Now, also write that thunder is the sound of that air moving so fast it breaks the sound barrier. So you're literally hearing that sonic boom from the air moving so fast. I mean, it's the same kind of thing that you hear when a jet goes by. If you've seen the Blue Angels or any other kind of air show with jets, when they break that sound barrier, you get that big boom, and that, again, is a rapidly moving pocket of air. How rapidly? Faster than the speed of sound, 725 miles per hour. So this air is superheated to 30,000 degrees and is moving so fast now that it breaks the sound barrier. Okay, so let's talk a little bit about thunder and lightning together. Remember that light travels at 186,000 miles per hour, while the sound that lightning produces only moves at 725 miles an hour. So you can see the difference here, right? Now, so you see that flash of light, that lightning, because it's moving at 186,000 miles an hour, but you don't hear the sound right away because the sound's only traveling at 725 miles an hour. So make sure you get that in your notes. So that's responsible for the time lag between thunder and lightning. It should be lightning and thunder, actually. So that's responsible for the time lag, is the speed that those things move. Now, a cool for your information type thing is there's a simple formula that people get it wrong all the time. So let's get that simple formula now for calculating how far the storm is that's producing this thunder and lightning. So you hear or you see a flash of lightning, you count the seconds it takes to hear the thunder. So then what you do is you take that number and divide by 5. So for example, if you see the flash of lightning and 15 seconds later you hear the thunder, you take that 15 number divided by 5 and you know that the storm is 3 miles away. Okay? 3 miles away. So that's the formula for calculating that. So this map then shows how often lightning strikes different parts of the lower 48 states. Write in your notes that Central Florida has the most intense concentration of cloud-to-ground lightning because it has a lot of warm, humid air from the Gulf, and that the North and the Pacific Northwest have almost no lightning because the air is so much colder and so are the lakes. You've got to have that source of heat. Okay, that does it for this part. So take a picture of your notes, submit them to Moodle, grab that Part 5 study guide, and I will see you next in Part 6. Bye.